For most of human history, we knew of only one set of planets, the ones that orbit our Sun: Mercury, Venus, Earth, Mars, and the giants beyond. These were our celestial neighbors, our only known companions in the vast, dark emptiness of space. We looked up at the night sky, at the countless stars twinkling like distant diamonds, and we wondered, were we alone? Is our solar system special, a rare cosmic jewel? Or is the universe filled with other worlds, orbiting other suns? This question, once the realm of poets and philosophers, is now a central quest for science. We are explorers, and the greatest ocean we have ever faced is the cosmic one. The answer began to unfold in our lifetime. We discovered that those distant stars are not solitary points of light. They are suns, just like our own. And many of them have families of planets. We call these planets exoplanets. The exo means they are outside our solar system. For the first time, we had proof. The universe is not empty. It is teeming with worlds. Billions and billions of them, just in our own Milky Way galaxy. Each one is a new place, a potential story waiting to be told. The discovery of exoplanets changed everything. It transformed our view of the cosmos and our place within it. Think about what this means. For every star you see in the night sky, there is a good chance at least one planet is circling it. Maybe more. Some are giant balls of gas like Jupiter. Others are small, rocky worlds like Earth. Some are so close to their star that their surfaces are molten seas of lava. Others are frozen solid, lost in the cold darkness, far from their sun's warmth. The variety is staggering, more than we could have ever imagined. Our solar system is just one of countless planetary systems, a single grain of sand on an infinite cosmic shore. This cosmic census of worlds brings us back to that ancient, profound question. If there are so many planets, could some of them harbor life? Could there be other places where the conditions are just right for something to grow, to evolve, to look up at its own sky and wonder? This isn't just a scientific question, it's a deeply human one. Finding life, even simple microbial life, on another world would be one of the most significant discoveries in the history of our species. It would tell us that we are part of a grander biological story, a cosmic story of life itself. The search is on. So how do we find these distant worlds? They are incredibly far away and impossibly faint. An exoplanet doesn't shine with its own light. It only reflects the light of its star. Trying to see an exoplanet directly is like trying to spot a firefly sitting next to a giant searchlight from miles away. It's a monumental challenge. For a long time, it was impossible. But human ingenuity gave us new ways to see, new methods to detect the invisible. We learned to look for the subtle effects a planet has on its parent star. We became cosmic detectives, searching for clues. One of our most powerful methods is called the transit method. Imagine a moth flying in front of a distant streetlight. As it passes, it blocks a tiny fraction of the light, causing the light to dim ever so slightly. We use powerful telescopes, like the Kepler Space Telescope and now the James Webb Space Telescope, to stare at thousands of stars at once, measuring their brightness with incredible precision. If a planet's orbit takes it directly between us and its star, it will cause a tiny, periodic dip in the star's light. A regular, repeating dimming is a telltale sign of a planet passing by, a cosmic blink. Another clever technique is the wobble method, or radial velocity. A star doesn't just sit perfectly still while a planet orbits it. The planet's gravity pulls on the star, just as the star's gravity pulls on the planet. They are dance partners. This causes the star to make a tiny circular or elliptical motion. It wobbles. We can detect this wobble by looking at the star's light. As the star moves toward us in its wobble, its light waves get compressed, shifting toward the blue end of the spectrum. As it moves away, the waves stretch out, shifting toward the red. This tiny rhythmic shift in color reveals the presence of an unseen planetary companion. These methods and others have opened the floodgates of discovery. We went from knowing of 0 exoplanets to confirming over 5,000 of them in just a few decades. Each discovery is a testament to our relentless curiosity. We have built extraordinary instruments and placed them in space, above the blurring effects of Earth's atmosphere, all to hunt for these faint whispers of other worlds. The hunt is a painstaking process of gathering data, checking for patterns, and confirming that what we see is truly a planet. Every confirmed world is a new dot on our growing map of the galaxy. With thousands of new worlds found, the next question is, which ones could support life? We can't visit them, at least not yet. So we have to start by looking for conditions we know are friendly to life. The most important ingredient, as far as we understand it, is liquid water. Here on Earth, wherever we find water, we find life. From the boiling vents on the ocean floor to the frozen deserts of Antarctica. Liquid water is a wonderful solvent. It allows the complex molecules of life to move around, meet, and react. So, the first thing we look for is a place where liquid water could exist. This leads us to the idea of the habitable zone. You might know it as the Goldilocks zone. It's the region around a star where the temperature is not too hot and not too cold, but just right for liquid water to exist on a planet's surface. If a planet is too close to its star, any water would boil away into space. If it's too far, the water would freeze into solid ice. The habitable zone is that perfect orbital sweet spot. Finding a planet in this zone is a major first step in narrowing down our search for life. It's like finding an oasis in the cosmic desert. The size and location of the habitable zone depend on the star itself. A hot, bright star has a habitable zone that is much farther out and wider. A cool, dim star, like a red dwarf, has a habitable zone that is much closer in and narrower. Our own Earth orbits comfortably within our Sun's habitable zone. Venus, our neighbor, is too close to the Sun, a runaway greenhouse inferno. Mars is on the outer edge of the habitable zone, a cold, frozen world today, though it may have had liquid water in its distant past. The habitable zone is a convenient guide, helping us prioritize which worlds deserve a closer look. But being in the habitable zone is not a guarantee of life. A planet also needs to be the right size. A world much larger than Earth would likely be a gas giant with a crushing atmosphere, no solid surface to stand on. A world too small might not have enough gravity to hold onto an atmosphere or liquid water. So, the real prize is finding a rocky planet, roughly the size of Earth, orbiting within its star's habitable zone. This is the trifecta, the combination of factors that makes a planet Earth-like and a prime candidate in our search for biology beyond our world. Our search has already revealed some truly tantalizing worlds. These are not just data points, they are real places, destinations for our imagination. One of the most famous systems is TRAPPIST-1, located about 40 light-years away. This star is a tiny, cool red dwarf, not much larger than the planet Jupiter. But orbiting it are not 1, not 2, but 7 Earth-sized rocky planets. This is an incredible discovery, a whole system of worlds similar in size to our own. It's like finding a whole new solar system of siblings to Earth, all huddled close to their faint red sun. What makes the TRAPPIST-1 system so exciting is that at least 3 of its planets orbit within the star's habitable zone. These planets, named TRAPPIST-1e, F, and G, could potentially have liquid water on their surfaces. Imagine standing on one of these worlds. The sky would be a perpetual twilight, illuminated by a dim reddish sun that would appear much larger than our own. The other 6 planets would be visible in the sky, some appearing as large as our moon, a spectacular and ever-changing celestial ballet. These worlds are close enough for our next generation of telescopes to study their atmospheres. Another fascinating candidate is Proxima Centauri b. This planet orbits Proxima Centauri, the very closest star to our Sun, just over 4 light-years away. That's our next-door neighbor in cosmic terms. Proxima b is a rocky planet, slightly more massive than Earth, and it also orbits within the habitable zone of its red dwarf star. However, there are challenges. Red dwarfs can be violent stars, prone to blasting their nearby planets with powerful flares of radiation, which could be hostile to life. We don't yet know if Proxima b has an atmosphere to protect it, but its proximity makes it a target of intense study. These are just a couple of examples from a growing list of fascinating worlds. There's Kepler 452b, sometimes called Earth's cousin, a planet orbiting a star very similar to our Sun. There's LHS 1140b, a super-Earth in a habitable zone that might be a prime candidate for a water world. Each of these discoveries adds a new layer to our understanding. We are moving from simply counting planets to characterizing them. We are starting to learn what these worlds might be like, piecing together clues from across light years of space to paint a picture of their nature. The gallery of known worlds is growing, and with it, our hopes. Finding a rocky planet in a habitable zone is just the beginning. The ultimate goal is to find actual evidence of life. Since we can't go there to collect samples, we must analyze the light that comes from these distant worlds. When starlight passes through a planet's atmosphere, or is reflected from its surface, the molecules in that atmosphere absorb specific colors or wavelengths of light. This leaves a unique pattern, a sort of chemical barcode, imprinted on the light. By capturing this light with powerful telescopes and breaking it down into its constituent colors, we can read this barcode and figure out what an alien atmosphere is made of. What are we looking for in that barcode? We're looking for biosignatures, signs of life. The most obvious one is an atmosphere rich in oxygen. On Earth, our oxygen-filled air is a direct result of life. For billions of years, plants and algae have been performing photosynthesis, taking in carbon dioxide and releasing oxygen as a waste product. Without life constantly replenishing it, oxygen would quickly disappear from our atmosphere. Finding a lot of oxygen in the atmosphere of a distant exoplanet would be a very strong, though not definitive, sign that some biological process might be at work there. But oxygen isn't the only clue. We also look for other gases that, in combination, would strongly suggest biology. For example, finding both oxygen and methane in the same atmosphere would be very exciting. These two gases tend to destroy each other chemically. So, to find them both coexisting in large amounts, you would need something constantly producing them. On Earth, that something is life. Microbes produce methane and plants produce oxygen. Finding this specific chemical imbalance on another world would be a smoking gun, a powerful indicator that the planet is not just habitable, but inhabited. This is the great work of the James Webb Space Telescope and future observatories. They are designed not just to find planets, but to sniff their air from quadrillions of miles away. It's an incredibly delicate task, requiring us to capture the faint light from these worlds and dissect it with exquisite precision. The search for biosignatures is the next frontier. It's a search for a chemical fingerprint that says, "We are here." Finding such a signature would mark a turning point in human history, a moment when we finally learn that the universe is not just full of worlds, but potentially full of life.